Any questions? Yes.
If we're unable to make it to the test tomorrow, would we be able to retake it? How would that-
You're really retaking it if you didn't take it the first time.
Right, would we be able to reschedule?
One would think so. There's precedence for it? You want a yes or no? Probably. It depends upon the reason. I did have a student years ago who didn't show up for a quiz just because he didn't feel like going. So, I appreciated the honesty. But it was very easy to grade. Someone else. Anyone else walk in since Genesis? I don't think so. All right. Other questions? So we've just begun. All right. At some point, I'm gonna need to go grab some props, but until then, let's get to the point where I need them. We've just done a bunch of transliteration of one formula into another. Let's talk about moment of inertia. I'm about to do a derivation, which of course is everyone's favorite thing to do. It's gonna look a little bit like alphabet soup up on the board. But hopefully, the reason for my doing it, well, ultimately, the reason for any derivation I do is just so that it's just not thrown at you, that you, whether you understand the derivation or not, you understand, this is where we started. I understand that there's some process to get there. As opposed to, someone just came along and made up this formula. What we're going to do is, if we're talking about rotating objects, I'm going to take a rotating object here, picture overhead view of the door or something like that, that's swinging like this. And I want to figure out what is the kinetic energy of the door. Oh, I was about to write it down. I don't have to write it down. All of you know it. Because I'm about to ask you, and you're going to say it in unison. It's going to be a beautiful thing. What is the formula for kinetic energy?
1/2 mc squared.
That wasn't bad. Not completely in unison, sort of in rounds a little bit, but hey, I'll take it. So, I have this door swinging. This is the axis of rotation. So this point right here is not moving at all, and this is moving the most. What would you choose for speed? Let's first establish why I would even ask that question. What's the formula, the basic formula for speed? Louder. Anyone else?
Distance over time?
Yeah, distance over time. Is that what you said?
Yeah.
Okay. So speed equals distance over time. So if I have, we will assume this is what's known as a rigid body. And that's a general assumption that we're going to make. I'm not going to have something where, part of it's moving and the other part's staying behind. Like if, like this, as I rotate it, all the particles are not moving together, that is not a rigid body. Rigid body, they all move together like the door. So if I look at, if this goes from here to here, so all I'm doing is just rotating it 90 degrees. Which part of the door moves the farthest? I thought somebody said.
Top part.
Yeah, the top part does. Because this has to travel all the way from here to here, and this part just moves there. So this is gonna be traveling at a much faster speed than this will. Now, some students have an issue with that, and they're going, yeah, but it's all moving together. It has the same angular speed. It doesn't have the same speed. So if I just say speed, this is the linear stuff, that's distance over time, just like Johanny said. All right, so which part of the door would you use to find the speed? If I want to find the kinetic energy, it's 1/2 times the mass times the speed squared. What part of the door would I choose for speed? All right, so you're aiming for up here? Everyone good with that, or someone have a different suggestion? You'd go for the middle?
Yeah, the average between the two.
They're good with those two suggestions? Someone else wants to say the bottom part, or? Why the top part instead of the bottom part?
Because it's moving the most.
And this isn't moving at all.
No, it is, but. What did you just say? Didn't you say that it has the speed?
Yeah, if I'm plugging into this formula, I need to figure out the speed of the door, so I was asking which part of the door should I choose to figure out the speed?
Oh.
You said that part. I think that said that part. I was suggesting, why not this part? I hope you realize that there's an issue, the fact that the speed is different. We could choose different spots. I mean, it is actually, you could come up with at least an upper bound. If I chose this spot, the part that moves the fastest, I could come up with, well, I know what the maximum value could possibly be. If I chose this spot, well, that'd be the minimum. Middle makes some sense, but it turns out the middle is actually not the best spot either. If we want to get an exact value, now if we're just doing approximations, fine, we can pick one of them. So let's just assume approximations. I heard top of the door first, so let's pick that one. So if this length here is L, then I would do 1/2 times the mass of the door times the speed of, I'll just write speed of top squared. But I hope you recognize it's not a great estimate. It's an estimate, it gives us a ballpark. I could get a slightly better estimate if I just broke the door in, if I treated it as two different objects instead of one object. I'd have the mass of this part and the mass of this part. I could choose the speed at the top of each section there. So I'd get a better approximation if I then did, well, it's the 1/2 of, well, half the mass because I broke it into two pieces, times the speed of the top half squared, plus 1/2 times half the mass, times the speed of the bottom half squared. This would get me a better result. What would get me even a better result? You look like you want to say it.
Split it into 3 parts.
Yep, why stop there? Why not 4, 5, 6? How many parts should you break it up into? Well, it depends on how accurate you want to be. What the math people do is they break it up into an infinite number of parts. We're not going to do that right now. We're going to break it up into, I'm just going to say n parts. N is just some number. So all I want is a marker to write dark. That's what I'm doing today. So my kinetic energy is 1/2 times the mass of one part times the speed of that part squared, plus 1/2 times the mass of the second part, plus the speed of that mass squared, plus 1/2 times the mass of the third part times the speed of that part squared, plus, until I have up to 1/2 times the mass of the nth part times the speed of that part squared. Where my mass 1, mass 2 is the mass of the individual tiny little pieces. Now, it might seem like we are getting a little bit, we went from doing just a simple formula to now we're adding up a whole bunch of them. It will simplify in a moment. All right, so when I got a bunch of adding up stuff like this, of course the math people got a simple way of writing it. So all I'm gonna do is I'm gonna write the same thing, except I'm gonna do it in a shorthand notation. I think that was the last question. So if you see this symbol right here, this just means I'm gonna add a bunch of stuff up. And whatever I'm adding up, there's a pattern, it's a 1/2 times mass of, I'm gonna put a little subscript I, times speed I squared, where I goes from 1 to n. This is just a shorthand of saying I'm gonna add up 1/2 mv squared for n number of pieces. For the inquiring minds, that symbol is a capital sigma. Now, that 1/2 there, every single term is multiplied by 1/2, so I can actually factor that out. So if I have something that's, if everything is being multiplied by something, I can just bring it out front and just multiply by what's left over. So that's the same as 1/2 times that sum of m sub I v sub I squared. Now notice I did not write I equals 1 and n anymore. It's understood to still be there. This is just a lazy physicist way of writing it, saying, yeah, that stuff still applies, I haven't changed that. Wow, this looks so much simpler, right? All right, let's see if we can take it one step further. Now, I mentioned that the objects on the outside there are moving. That's moving faster than this part is. And this is moving somewhere in between those speeds. I know that the distance that it travels is just going to be the distance that it travels is, let's just say it goes around an entire circle. What is that distance called? Ashlyn?
Circumference?
Yep, you remember the formula?
No.
Anyone remember the formula for circumference?
Pi r squared.
That's it. There are two formulas for circles. That's the other one. That's area. The other one. So close. It's 2 pi r. All right. So the circumference is 2 pi times whatever the radius is. So if I wanted to figure out how fast this thing was traveling, if it goes around a circle once, then how fast it's going, the speed would be the distance traveled, which is 2 pi times the radius divided by how much time it takes. I use a capital T here because if I'm talking about something going all the way around, completing a cycle, then the time is called the period, symbolized by a capital T. So this capital T stands for period. All right, so I have this thing traveling around in a circle, the speed, distance over time. Now if I want to talk angular speed, because remember we did that transliteration last time of, here's the linear equation, what would the other equation be? What would the rotational equation be? Well, if V equals delta x over delta t, then omega, the angular speed, would equal what? Look back at your notes if you need to. Think of what is the analog of x and t.
Theta over T.
So it's the change in the angle over the change in time. So if I talk about this thing going all the way around in a circle, what's the angle that it goes through?
360
I need units.
degrees.
Yeah, 360 degrees. How much time would it take to go all the way around? Not looking for a specific number here. Is it? Jason, looks like you want to say it.
T.
Yeah, T. That's it. Big T.
Big T.
Now you said 360 degrees. So the angular speed, 360 degrees over the period. However, 360 degrees really is not the preferred unit here. Have I done the radian talk? All right, let's talk about radians. We will come back to this. In the, I think primarily 18th and 19th century, mathematicians made a big push to try to get rid of all of the man-made stuff as possible. They wanted what was pure mathematics, that which is based upon the way the universe was created, not based upon what people have put onto it. I think it's out of that you suddenly get someone going, why is 1 + 1 = 2? And there was a 2-page proof for that. And then a guy named Kurt Gödel came along and blew a hole in that one. So now the proof that 1 + 1 = 2 is 100 pages long. And I'm sure you realize now that the foundation of your whole mathematics can be explained, and you should all be feeling at ease. However, where do we get 360 degrees? Who is to blame for 360 degrees in a circle? Not me. It's those pesky Babylonians. They had a base 60 system. Now, it might seem strange, we're on a base 10 system. They want a base 60 system, which might seem odd, except in our language. 60 is divisible by 1, 2, 3, 4, 5, 6, 12, 15, 20, oops, sorry, lost one, 12, 10, there we go, 12, 15, 20, 30, and 60. So it's divisible by a bunch of numbers, which makes it convenient in terms of doing mathematics, especially when you don't have computers or calculators. So 60 was very special to them. They also recognized that there was something special about the equilateral triangle, where all the sides are equal and all the angles are equal. So you just marry those two things, and so that is a 60, 60, and 60, which we now call degrees. Now, if I take 6 of these and I put them together, usually better than that. Let's see if I can. So I'd have 60, each of these angles would be 60. And so if I go all the way around, I got 660s, I got 360. That's where it comes from. Stemming from what I think ultimately was the religious beliefs of civilization thousands of years ago. So they looked at that and said, that's clearly man-made. Is there something that is true for all circles so that we can come up with a new unit system here? And so they recognize that if I take a circle, all circles have a radius. So imagine I've got a circle here and I've got a piece of string that's the length of the radius, and so then I start wrapping that radius around. So I take that and I sort of wrap it around so that this right here, it's called the arc length, so that the arc length is equal to the radius in length. They notice that this angle right here was the same, no matter what circle you pick. If you take its radius and start wrapping that around the edge, that angle would always be the same. And they thought, that is not man-made. That is the way nature is. And so they said, this is 1 radian. Or for those who don't feel like writing the word out, 1 rad. Well, they felt pleased with themselves on that day, I'm sure. The next question is, how many radians are there in a circle? Well, how many times can you wrap a radius around the outside?
6.
And a little bit. Matter of fact, 2 pi radiuses to go all the way around. So in a circle, that 360 degrees is actually the same as 2 pi radians. And I'm sure all of your calculators have radians on them. Occasionally you get units of gradians. It's been a while since I've seen it, but I have seen calculators with gradians. That is, there are 400 gradians. I've never actually had to use it, other than it was a button on the calculator way back when. All right, so we now have this thing here, so that if I'm going all the way around in a circle, instead of 360 degrees over the period, it's 2 pi over the period. That almost looks like this, except for the fact that I got that extra r there. So if I put in omega here instead of 2 pi over t, I get v is equal to omega r. And that is the relationship between linear and angular speed. Questions there, because I'm about to combine that with this whole kinetic energy stuff we were doing.
Why at the top it's not